Amazing. Thank you so much for that generous introduction. And I would like to also thank everyone joining us here on this call from different part of the world. Thank you so much for joining us this day to, to learn with us as we explore what it takes to think like a process engineer. And I actually want to thank the executive of the NSChE Chemical Engineering UNILAG chapter. Thank you so much for putting this together. I'm so grateful. I'm so excited to be here with you guys. All right. Now, before I say anything about chemical engineering process, I need you to do one thing right now. Everyone on this call, I need to do one thing. Can you go to your browser, um, whether on a phone or your iPad or your laptop? Do me one thing, just one thing. Can you go to www.lensasim.com? And you just go to your browser and just do that. That's all I need you to do. It's going to be very important for us as we explore this training together. So if you have done that, can you just drop something on the chat for me to know, maybe just an emoji or a like, just www.lensasim.com. Okay. Okay. Now the next thing is that, do you see my screen? Do you see my presentation slide? Okay, great. All right. Thank you. Thank you. All right. Amazing. Amazing. All right. So I haven't done that. Let me throw you to a real engineering scenario right now. Real engineering scenario. And I want you to imagine with me as we think through this together. Imagine you are like 7 months or 8 months into a job in a petrochemical facility or a refinery, and you are the process engineer on floor. And your plant manager walks up to you and say, the feed pressure has dropped by 15%. If we continue like this, our output will fall below spec. We will lose $10 million. Fix it. What would you do? You are the engineer. You said you have your qualification. You've shown I am the best in this, in that. You've written a strong resume. We've interviewed you and you are working with us for 7 months. And then there's a real problem that is facing the plant. And then they said, do this. Now, actually, the way we respond to those type of situations, I have been able to classify engineers into two main groups. One set of engineers will do this. Okay, let's fix this problem. So they wear their hard hats, they wear their safety boots, they walk straight to the plant floor, and then they look for a valve that somebody has mentioned that if you want to do this, just turn this. So they turn the valve, praying and hoping that the catalyst will not overheat and blow up. That's one set of engineer. The other set of engineer will do this. Let me take 10 minutes and build a steady state model. So with that model, after running that simulation, I can find the new operating boundaries, which will help me to determine the exact equilibrium set point at which the product is stable before we make any decision. What type of engineer are you on this call? Can you drop something on the chat? Let me know. Are you the engineer that will just go and say, you know what, let's go and fix it? Or are you the second engineer that will say, let's develop a model before we do that? Can you drop something in the chat to me to know that you're listening or you can get me? Thank you. Thank you. Thank you, Moses, for being that honest. And that's what happened. People just make decisions. Now, irrespective of the discipline that you are, whether you're a chemical engineer or a mechanical engineer, or you are even a professor, wherever you are that you are joining us here right now, what we want to achieve today is to think like an engineer, a real process engineer. Today is not a day to do complex mathematical equations and all of that. That's not what we are doing here today. What we want to do today is how do we really come up with models that are accurate enough for us to test and confirm that the decisions we are making is data driven. One of the skills that will separate you as an engineer on floor is that you make data driven decisions. And so that's what we want to do here today. So we want to see how we can use steady state models or simulations and be able to predict problems correctly. All right. So as important as this is, now let's see, why do we even actually simulate? Why should I develop a model if I run into a problem? What the good thing I want to let you know is that simulation would help you to be able to test conditions properly, right? Without risking people's life, without wasting company money. Just imagine the scenario I painted earlier, right? If you make the wrong decision, you could even blow up the plant. So what process simulation helps you to do is to be able to help you to do what we call testing proof of concept, right? Testing models that you have, test extreme conditions, and decide which one is the best to do at a time. What process simulation will also help you to do is to move away from complex mathematical equations that you learn and then begin to make data-driven decisions. Because in the industry, right, one of the things that was not that I also want to let you know is that before we even build LensaSim, I have had several years of experience, right, working in industry as a process engineer. So I know what differentiates real engineers and the ones who just imagine things and just do it. So it's going to take you away from dry textbook concepts and then be able to make real data decisions that will change life and transform the world. And one important thing, especially for those who are still students who are joining me on this call, right? Process simulation is going to help you to gain that skills that will make you employable. So that's why we simulate, like test conditions, make sure that conditions are within the right operating conditions before we ever build that plant. Okay, amazing, amazing. Now, having seen the importance of process simulation, one of the things that we've noticed is that students are short out of these skills, especially because of how expensive it takes to get this license. These licenses are very expensive. Most students don't even ever have to use it. And I tell you my story, right? Like you said, I finished from the Department of Chemical Engineering. I actually went through UNILAG. It was in my final year that I started trying to do simulation, and there were some people who came to just run some training for us. Even at that, we didn't even really have the access. We didn't have opportunity to test it more and be able to use these simulations, process simulation, and develop these skills that will help us to make us employable. So we see the problem of accessibility, right? And another problem that we have is that apart from having access to this simulation, how easy and friendly is it for you to use? How do you really understand how to use it? And that's what led us to develop and what we call LensaSim, right? Our product. That's why we made LensaSim today, because we're trying to solve the problem with accessibility, because many people don't have this access, if you agree with me. And then even those that have it, they don't even know how to use it correctly. So we've developed a kind of process simulation that is browser based. So we brought process simulation generally to everyone, even from your phone, you can simulate. Though you can run process simulation from your phone, you can run it from any device, any type of apples or any type of device that you might have. So we dealt with that problem with accessibility, and the other problem we dealt with now is how do we make this easily available for everyone to understand. Okay, so remember I gave you 4 stacks, right? The 4 stacks I gave then was to go to www.lensasim.com and open that on your browser. Good. Now, if you have done that, the next thing I would like you to do is to try to sign in, right? So you go to the website and try to sign in. So let me show you what I'm saying right now. I will stop sharing my slide and then I will share. If you are still following me, can you just drop an emoji so I know you can see me? Amazing, amazing. Good. So that's what LensaSim is here to achieve, right? We've dealt with the problem with accessibility, right? We're trying to make sure that everyone has opportunity to test these skills and have these skills that make them employable. So we actually be able to make LensaSim. So you see, this is what we have. So after you open it, the next thing, because like I said, it's going to be, we want to make it practical, right? This is not a theoretical that I'm going to be deriving math and no, no, no. That's not what I want to do. We want to do this together, develop these skills and make ourselves employable. All right. So if you've done that, the next help I will need from everyone on this call is to try to sign in. So, okay, let me sign out and sign in. So you just follow me along. So okay. All right. So you see the sign in button here. You just click sign in, right? And you put your email. So me, I'm putting my email, ibeh@lensatech.com. So when you do that, it generates a code for you. That code, just go to your email and pick that code. Okay. So I will take the code now. I would log in. Okay, right. So you see, I am now in Ibeh. So if you've logged in, can you just drop? Oh, yeah. Thank you. Thank you. Thank you. Thank you, Moses. Yeah. So you can use any email, right? The beautiful thing is that you can use any email, your Gmail, any email that just go in and then just log in. You get a code, it gets sent to that email, and then you log in. Okay. So if you log in, just drop something so I know you're following me on this call. Okay. Amazing. Thank you, Williams. I see you, Moses. I see you, Nulu Ababala. Amazing, amazing. I see you, Dokas. I see. Awesome, awesome. Now, don't forget what we want to do here today. We want to develop a skill that will make us employable. And we're going to use that skills to test some models, right? Amazing. Okay, good. Now that you're already in the simulation environment, what are we going to simulate today? I would go back to my slide. I will go back to my slide so you see what we want to do today. What do we want to test today? Okay. Do you see my slide? Good. All right. So having opened the simulation environment and we have stressed the importance of these skills that we need, today we want to try to simulate a Fischer-Tropsch process. Now, I want to believe everyone understands what Fischer-Tropsch process is, but just for the sake of just emphasis on just saying it again, Fischer-Tropsch process is a process we use to convert syngas to liquid hydrocarbon. That's it. No more, no less. We're going to take a syngas and take it to liquid hydrocarbon. So a syngas, what's a syngas? A syngas is a combination of carbon monoxide and hydrogen. And you get that from, steam reforming, right? You get that from steam. So the whole process of Fischer-Tropsch process is what we call gas to liquid. So you're taking a gas, syngas, and then you want to take it all the way to make liquid hydrocarbon, like your diesel, your jet fuel. So that's what we want to do today. We want to build a plant that is capable of producing liquid hydrocarbon from syngas. That's what we want to do. Simple, easy. And I've chosen this because it's going to demonstrate a lot of things for us, a lot of concepts. We're going to see different part of the equipment, right? Different part of the plant. We're going to see reactions, going to see everything. So I just feel that this would help us to understand what we need to do. So we take a syngas, don't forget that, syngas, and then take it all the way and make liquid hydrocarbon. And then from there, we're going to begin to test models and see, okay, if I change this, what will happen? And that's where the engineering comes in, right? Engineering is not just, an engineer is not an operator that you say, go and do this. No, an engineer comes and thinks of concepts, tries them, and then see what will be the outcome. So that's what we want to develop, that skills of curiosity and that skills of data-driven decision that will help you to become so employable. All right, Fischer-Tropsch process. Do you understand? If you understand, just drop something. I want to be sure that you get all I'm saying today, because you want to leave here different. You're not going to go back the way you came, because today is Saturday, right? You should have been doing something else. So you're going to need to develop a skill that is very helpful for you. So the first thing you've developed now is that you know that there's LensaSim available for you to explore and then test it. So now let's use that to build a plan that can produce liquid hydrocarbon. Okay, now let's leave our simulation environment now. And sorry, let's leave our slide, I beg your pardon, and then go to our simulation environment. Okay, I'll share this again. I'm going to walk us step by step, right? Just so you get what we are doing now. All right. So if you are here, the next thing you need to do is to open a simulator. You see here. So when you click this place that says open a simulator, it opens a new tab. It opens a new tab. And I will share my screen now I'll share my screen there so you see what I'm saying. Once you click that, it's going to open a new tab. Do you see this? Do you see my screen? Are you here? If you are following us, are you here? Amazing. Thank you, Ido. Thank you, Babala. Thank you, Tomiwa. Amazing, amazing. You guys rock. I don't want to steal the show and say, because there's something special about like greatest are cokites. If you are not from UNILAG, don't feel bad. UNILAG is University of First Choice. We are first in everything. So we'll get it done super fast. Thank you. All right. So this is where we are now, the simulation environment, right? Telling us what we need to do. So you can see that. Okay. Fischer-Tropsch process. I think it's very important I really explain what we need to build more, even though I've explained to you that it's a process that takes syngas to liquid hydrocarbon. Let me show you a kind of PFD to show you how it's going to look so that you can follow me along, right, as we explore this together. Okay. I would apologize that we're sharing multiple screens, but I think it's important that we all get this well, and then it's important that we all get this very well so that we know what we are doing. Okay. So I have developed a kind of a manual, right, that would help us today. Usually you can get all this information you need from the internet. Now, let me know if you see a Microsoft Word that is open. Do you see that? Awesome, awesome, good. All right, so you can find it. So I've developed this specially for today's class so we can all walk through and understand the process. And again, you're going to understand why we are doing what we are doing. That's what we want to achieve. So if you see this PFD here, I'm going to make the simple case in the interest of time, but okay, maybe subsequent webinar, if opportunity comes, we can make a more complex Fischer-Tropsch process. But just to stress something, I'm going to make just a simple process that takes the syngas and make liquid hydrocarbon. Now, this is the feed that's going to come in that has the carbon monoxide and hydrogen. It may have some other trace gases that we don't need. So the question is, after I have the syngas, the next thing is that I need to compress it. I need to compress the gas. Why? Why don't I just take the gas and then just take it straight and run reaction? Now, the problem is that the reaction itself is a type of reaction that involves a decrease in volume. So if I'm coming at a particular feed condition, for this case of learning, I'll show you the condition. The condition is like a syngas that is coming with an inlet temperature of 35 degrees centigrade and a pressure of 10 bar. So I will need to compress it to higher pressure so that it can, because the way the reaction, I'm sure you all remember, you guys are amazing chemical engineering students. So you know that the type of reaction that goes is a reaction that involves a decrease in volume. So for me to ensure that the reaction proceeds forward, I just need to increase the pressure. Do you understand? The syngas must go to a compressor because I need to increase the pressure so that the reaction can move to the direction I want it to go. Amazing. Now, after compressing the gas, remember the gas is coming at an inlet temperature of 35. I need to heat it up. Why? I need to heat it up to a particular temperature that it can get to the catalyst activation temperature, because the bond between carbon dioxide and oxygen is a triple bond. I need to be able to break that bond. So I need to heat it to a high temperature enough. For in the case of this, I'm going to heat this inlet syngas to a temperature of about 220 degrees centigrade, such that it's ready to go into the reactor. I don't think I need to explain more about, about a reactor, right? A reactor is going to cause reaction to take place. So reaction will take place. I produce my products. After I produce my product, I will not take it to cooler, because the outlet temperature that is coming out is 220 degrees centigrade. I can't feed that directly to the separator. But again, we're going to test that. That's what we're going to, don't just agree with me. You can, that's why when you build your model, you can also play around and say, let's ignore what Dr. Ibeh Omodolor is saying. Let's just put a specific temperature. So that's what engineering, that's what simulation gives you opportunity to do. It helps you to satisfy your curiosity, because you can't go to a live plant that's already working and say, let me just change the temperature. You are going to blow up the plant. So, but from simulation, you can play along that and develop your curiosity skills. Correct. All right. So now, once the reaction comes out, it's coming out at a very high temperature. I need to cool it back down to 40 degrees centigrade. Cool it back down to 40 degrees centigrade. Once I cool it back to 40 degrees centigrade, then it goes to a three-phase separator. Why do we need a three-phase separator? Because the product that we are producing is almost like as if it's in three-phase. You get? So the product is like as if it's in three-phase. The product has, you have a gas, you have the liquid hydrocarbon, and then you have water. So it has three-phase mixture. So this three-phase separator will help us to separate it. Do you understand why we have what we have? Feed here, the syngas, we need to compress it to a high pressure enough to get that. After that, we need to heat it up to a temperature that will overcome the activation barrier that we're going to try to deal with. And then we heat it up, the reaction takes place. After the reaction takes place, we have to cool it up to a particular temperature that is good enough to go to the separator. And when you get to the three-phase separator, the three-phase separator carry out three-phase separation. And then we have our product. We have the unreacted gas, we have the liquid, and we have that. Amazing. Okay. Now that you understand that, I have conditions here that would help us to build this. Okay. After this teaching, I can make this available to you guys. If you want to play around with all this, I can make this available to you guys. I can talk to the executive, the one that can send this. Like again, I said, I specially prepared this for you. That's how special you people are. I specially prepared this for you so that we can work on this together. Right. So if you want, we're going to share this document to you so you can play around with it. All right. Amazing. Okay. So now that's all the conditions, I'm going to be using these conditions because I may not be, because I'll be sharing the screen, but I will try to say those conditions out loud so you hear me as we're building this together. All right. I've explained the PFD itself already to all of us now, why we need what we need. Now is to now actually build the plant. So let me go back to my LensaSim. Let me go back to LensaSim. I'll go back to LensaSim now. So I'm back to my simulation environment, right? I believe you see that. Amazing. Thank you. Thank you. Okay. So after you get to the simulation environment, the first thing you need to specify is the component that you want to build, the component, the feed component, as well as the product component. Everything has to be specified in the simulation environment. You have to specify the feed and specify this. For the case of this that we're trying to, remember we're trying to do, I'll keep saying it many times so it kind of stick. So we're trying to do Fischer process. We're taking syngas to liquid hydrocarbon. So we have many things to specify. So the first thing we're going to specify is the component itself. So what are the components? We need to specify hydrogen. So you look for, there's a search bar here. You just search hydrogen and you select hydrogen. Now, what will be the next gas that we need to select? Syngas, carbon monoxide, and hydrogen. So let's get carbon monoxide also. we'll put carbon monoxide. Because the feed that we have, most times they're not pure syngas, right? They still have some, some other trace. So we can put carbon dioxide also. We need to select carbon dioxide also. So hydrogen, carbon monoxide, carbon dioxide. Then we need to select nitrogen. Nitrogen. Now, if you're asking me, why do we need all these? Like I said, the gas itself is not really a pure syngas. It will have some other trace equipment, trace gases. So we have hydrogen now. I selected hydrogen, I selected carbon monoxide, then nitrogen, then water. Water itself. Water. We select water here. So you can type in methane. Remember that the syngas is gotten from steam methane from, yeah, you do steam. So methane, and also methane is going to be part of our product actually from this. But anyway, so you put methane, you select methane in also ethane. You put ethane here. Ethane. Ethane. So hydrogen, carbon monoxide, carbon dioxide, nitrogen, water, methane, ethane, propane. 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 Well, apart from chemical engineering, I love petroleum engineering so much. One of the things that needs to be mentioned that I had my master's in petroleum engineering. So I had a BSc in chemical engineering. I have a master's in petroleum engineering from Institute of Petroleum Studies in Port Harcourt. I had a master in petroleum engineering, IPS. If you know IPS, that's where I finished my master's. Then I had my PhD in the US. I still live in the US. So I am a mixture of those three fields. Those two fields, I beg your pardon, chemical engineering and petroleum engineering. All right. If time allows, I will tell you why after chemical engineering we decided to go to petroleum engineering, but that's for another discussion. Let's focus on what is important. Why I went to do a master's in petroleum and why I now came back to chemical engineering. It's a very funny situation, but but I love petroleum and I love chemical engineering. All right. So I have selected propane. So the next thing, because we are going to now start making other liquid hydrocarbon, is that we're going to have next thing is butane. Butane. So I can put my butane here. But for this butane, we're doing normal butane at this time, not the isomerization product. So normal butane. And then we have hexane, N-hexane, normal hexane. Okay. Normal hexane. Then decane. 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 Then the last component that we need to select is hexadecane. 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 Okay, good. Now I've selected everything I need to select. All my components are fully specified. So one good thing that you will need to learn, and I want to quickly show you about our simulation, is that if you are new, you have a guide on here. It can guide you. I can turn it on and turn it off. So the guide will guide you if you're like the first time user. It guides you on all the stages that you need to go through. Anyway, so the first thing it will tell me is that specify the equipment which I specified. The next thing is the property method, but because of the type of reaction we're doing, Penrobison is the one that we can select. You can say, no, I don't care what this guy is saying, and then you can try Roth law. That's why you're an engineer. Don't accept. So you can play around with these things, but you come back to oh. Oh, okay. Thank you for that. We would, yeah. Well, we made, well, okay. My team already responding to you, so my team member would let me focus. My team member would take care of that, and they will explain. Maybe at the end I can explain why you may not be able. But even if you don't, just specify what your free access will allow you to specify. Okay. All right. Now you have everything. So Penrobison equation, and then the next thing you go is continue to simulator. Okay, amazing. You see my screen. So now we've done two things. We specify the components. After that, we have now choose the property method that we want, which is Penn-Robinson. And then now we are here now at the simulation environment now to now start the simulation. Remember what I said, that the first thing you need to do is that the feed. And you see how my guide is also leading me. So I will use the guide because I want to, for the process of the fact that most of us are using our software for the first time. So I will keep the guide on. So the guide kind of walk us through the process. And then where we need to change, I will change it. All right. First thing is the feed. So I just drag the feed from here and bring it to the simulation canvas itself. So this is the feed here. You can move it around as you want. So I have my feed. Then if you notice, it's telling me that I need to specify the feed condition, right? So let's do that. Let's specify the feed before we add the equipment. I'm sorry that you don't have the document. I will see a better way to help you guys to do but anyway, the feed conditions, we need to specify the feed condition. So let me specify that first before building. And there are many ways you can do this, right? There are many ways you can decide to do this. You can build the whole process flow sheet first and then begin to specify the conditions. But this for today, but that's how I do it for today. I'm going to change the strategy. Let's specify as we move on. Okay, all right. Now let's specify the feed. If you see, what is very important is the hydrogen. I've done all the calculation of what we need in terms of the balance, the carbon balance. So let me just put them there. For hydrogen to be 0.67 of hydrogen, I can say it out loud. So you can just add that here. Hydrogen here will be 0.67. Yeah, today is not a mass class or calculation class, or I've explained how we got that, but let's just, in the interest of time, hydrogen is 0.67 and carbon monoxide is 0.31 here. 0.31 here. So I put that 0.31 here. And then, like I said, there are trace amount of other gases that we're going to have in the process of this, trying to do this. So another one we can have maybe CO2. I'll put CO2 0.03 of CO2. Just a small amount, 0.03 of CO2. One other one I'm going to put is nitrogen, 0.006 of nitrogen, 0.006. Maybe let's make this very good for us to follow. Let's make this 0.03, 0.06. All right. Okay, so what we need to do is now the total flow needs to also be specified. The total flow for the course of this study will be 313 kilomoles per hour. The feed temperature that we are coming in was going to be 40 degrees centigrade, right? Remember we talked about that. And the pressure, so here you can, select the unit that you want. You can change it to any unit that you want. So I'm going to be using bar for today and an inlet pressure of 10 bar. So, okay, let's go back. It's something I did not do. We need to normalize it here and make it 1. So I've normalized it. Okay, good. All right, that is easy enough. Let me turn this guide off a little. We'll come back as we need it. Okay, remember feed first, right? We'll specify the feed. If you remember, what will be the next thing that we'll put? Let me share if you remember what I explained before. You have a feed gas that's coming at 10 bar. Remember I said we need to do something first before. Can you drop in the chat? Let's show that you are a student that are remembering what I'm explaining. What would be amazing? Oh, thank you. Excellent. So now we need a compressor. We need to compress the gas to the specified condition that we want. Good. So I need to look for a compressor here. So you see there's a compressor here now. I'll take the compressor and I'll bring it here. So you need to now connect the feed with the compressor. So when you want to connect it, you see an arrow and the compressor is connected. Boom. After connecting the compressor, we need to specify the condition of the compressor. Remember I said we want to take it from 10 bar to about 21 bar, right? So the compressor needs to be specified as 21 bar of outlet pressure. So change this to bar and change this one to 21 here. Good. Done. So after compressing the gas, what do you need to do? Let me see if you remember. You've compressed it. Remember I said you need to do something before the reactor to be able to take place. Do you remember what we need to do? Awesome. Wow, you guys, smart, smart. So we need now put a heater. So I need to look for a heater somewhere here and take it here. Then I need to connect the heater outlet. Sorry, I beg your pardon. I need to connect the compressor outlet and then I need to heat this reactor up. So when you go there, it's telling us that we need to specify the outlet temperature and as well as the pressure drop. All right, so let's get to that. So we need to heat it to 220 degree centigrade and the outlet pressure is 0.5 bar. So let's put that in here. The temperature is 220 and the pressure drop here should be 0.5 bar. Okay. You can try something else. So you can try something else. So don't completely, use exactly what I want, but this is just like a guide. But maybe when after this class, you can also try something else. Okay. All right. Now we have the heater. Now we've compressed the gas. We're heating it now. So where does it go next now? After we've heated it up. Awesome. Awesome. You guys are fantastic engineers already. Amazing. Now that we've heated it up, we need to now do the reaction itself. We need to do the reaction itself. Okay, so let me put the reactor now. So for the case of this class, to simplify the process, I'm just going to take a conversion reactor now, just a conversion reactor, just to convert it. So this is where I picked my reactor, a conversion reactor. So just connect the outlet here to the reactor. So the reactor is connected, but the reactor is telling me that I have many things I need to specify. I need to specify the reaction, and I need to specify the base limiting reactant. I need to specify the conversion I want and all that. But yeah, I have all of that. I'll just say that out in the interest of time, sorry. So we can meet up with everything. We're still in one phase, right? We need to build the plan. Then we are not going to begin to test model to think like an engineer. So let's move on quickly to that. We have specified everything now. Now we need to go to the reactor itself. So the reactor temperature, remember we've heated it. So you put, okay, good. So now we need to specify the reaction components that we need. We'll put all of them here and all of that. So let's do that. I'll call that out, sorry, because of time. Okay, so one thing you must remember is that the reactor, the reactant that is decreasing will be negative, correct? While the product will be positive. That's what is important here, based on the reaction stoichiometry, right? So the reactant itself will be decreasing. So let's take carbon monoxide, which is our limiting reactant. Carbon monoxide will be -1 here, -1 here. We'll put carbon monoxide there. And then the next thing I'm going to put is hydrogen. Hydrogen is also a reactant. Hydrogen should be decreasing, -2.26. All these values are calculated from carbon balance. I'm sure you guys know all this, so I don't want to spend too much time on this. Then water is +1. Let's put water here. Water is +1. There are many reactions that take place in Fischer-Tropsch process, up to 7 reactions, but I've simplified it to just a simple 1 reaction. So please, because of time, but there are many reactions, but let's just simplify it to just 1 reaction itself now. Okay, so we specify carbon monoxide, specify hydrogen, specify water. Let's specify methane. Methane is like 0.1, so we'll just say plus 0.1 methane. Good, plus 0.1 methane. Ethane plus 0.025 of ethane plus 0.025 of ethane. Like I said, I'll send this to you guys. You can play around with it again after this class. So we specify. So the next one is propane, 0.0167 of propane, 0.0167 of butane. This is positive. It's a product. Products are positive, reactants are negative. That's all that is very important here. And then N-butane is 0.0125. This is plus 0.0125 here. And then the N-hexane is plus 0.025. The N-hexane is plus 0.025 of N-hexane. Okay, decane, again, same thing with N-hexane, 0.025 plus 0.025. Then the last one we need to put in here is the hexadecane, 0.0219, 0.0219, 0.0219. This is plus 0.0219. Okay. Our limiting reactant is carbon. Okay. Okay. My team will respond to you. Carbon monoxide is CO here. That's our limiting reactant. Okay. Well, you know what limiting reactant is, right? But for the case of this, the limiting reactant is carbon monoxide, right? And then we want to do a conversion of about 0.7, 70% conversion. Okay, let's specify the pressure drop here of the reactor now. The pressure drop of the reactor, just 1 bar. 1 bar of pressure drop of the reactor is 1 bar. So remember that this is in bar, and put 1 bar here. Okay. Pressure drop 1 bar. The conversion is 70%. I've specified the whole conditions and all of that. So now after the reaction takes place, remember we have the product now, and the product is kind of really hot. And like I said, we can't take a product that's about 220 degrees centigrade and just put it in the 3-phase separator. So what do we do now? Very hot product that is coming out. What do you think we're going to do now? Can you drop in the chat? Let me be sure. Amazing. We're going to cool it. Thank you. Thank you. We're going to cool it. Awesome. So I need to put a cooler here. I take a cooler and put a cooler here and connect the reactor to the cooler. And the whole aim of the cooler is to be able to cool it down to a temperature that is reasonable enough for the 3-phase separator to work with. So we're going to cool it back down. Okay. Let's cool it to 40 degrees centigrade back, and then the pressure drop about 0.5 bar. So let's cool it back to 40 degrees centigrade. You can put your 40 here now, and then change this to bar, and the pressure drop of 0.5 bar. Again, you can get all this information from literature. That's part of what chemical engineers do, right? You research and get information. But again, I have a document I've prepared that I'm working with. All right, we've done everything. We've certified the feed, we certified the component, we put the heater, reaction took place, we're cooling it. Now we need to separate, right? I said it has a mixture of, it's like a 3-phase, right? It has the unreacted gas, we have the liquid hydrocarbon, then we have the and the last one that we have is the bottom, the liquid itself. So we need a 3-phase separator. So I'll look for a separation here. So these are our 3-phase separator. In LensaSim, we've developed a 3-phase separator that I can use. You put it here, connect this to your 3-phase separator. So a 3-phase separator condition needs to be specified. Also, we need to specify the temperature and the pressure of the 3-phase separator. If you are following me so far, just drop something on the emoji and we'll know that you are with us. Amazing. Awesome. 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 So the 3-phase separator is going to be, we have cooled it. So the outlet, the temperature that we're putting now is going to be 40 degrees centigrade, and the operating pressure will be 90 bar. So put your temperature here as 40 degrees centigrade. And then you put your pressure here in bar. Consistency is very important, right? Don't put one in bar and put one in kilopascal, except you are sure that you've converted them correctly. Yeah, these are some of the mistakes I also have made when I'm not consistent enough. All right, so now that we have the three-phase separator, everything here, so we need to put the product. Yes, we'll put the product. We'll put the product. Okay. All right, so you come and specify the product here. So you need to put the product stream. You connect. So it's because it's three-phase, there'll be three products, correct? So put this one here. You take another product. Put this one here. You take a third product and put this one here. Three products. Okay. All right. So if you put your guide on now, it tells you you've done everything. All you need to now is to simulate and see if our condition makes sense, right? So see, does it make sense what we've specified so far? Will it converge? If it does not converge, we need to troubleshoot. If you're happy, just drop an emoji. Super fast. 10 milliseconds, converge. What have we tried to do today so far is to make, this is a simplified form. I can see people asking questions, why the type of condition, why the timber? This is a simplified condition because in a more complex Fischer-Tropsch process, we need to now connect a recycle stream, right? And take this recycle back to the feed, put a mixer here that mixes the feed and that. But for the case of this, I don't want to run into that. But you see how fast you can build a system really quick. How fast now? We have a plant right now. Let me turn off the guide. We have a plant now that is capable of taking a syngas and produce products. So how do we interpret this data? What does it make sense? Now, the first step has been solved, right? The first step is that we have been able to successfully simulated the process, and then the process actually converge. So that says first step, but not the final step. The second step is to ask ourselves as an engineer, does it make sense? Is it actually doing what we expect it to do? Is it producing some product? Is it producing? Those are the level of critique that you need to have as an engineer. So anyway, so what we can do is that we can change this unit to, let me change it to mass flow. Change this to mass flow so we can see what we are doing. Okay. Thank you. You know, the beautiful thing is that, okay, yeah, if you must have anything as a computer, have a touch screen. You're able to move things easily and move things, you know, easily for you. All right. Okay. Now let's see our products. I have built a very simple process today, not super complicated, just for teaching process. If there's going to be another time for us to talk again in this webinar, it's going to be something really complicated. So, but I just want to lay this foundation for us. All right. So these are the products we have. S6. This is the feed. This is the product S6, S7, and S8. Remember, we can change this. You can rename them as you want. You can just rename it to whatever that you like. You change the name. But let's just play around. We're students, right? We can try many things, but you'd have used industry standard to specify it in a way. But you can just say syngas, whatever that works for you. That's what I want to achieve today, or feed or whatever. But there's industry standard on how to name all this, not just random. But student, right? We can also play and then follow up with industry. What I want to do today is to make you challenge things, right? Don't just accept that this is how things should be. You can play around with your own, but then still follow the standard that the industry has produced, okay? In the interest of class, you can play around, but in real world, when you're operating the plant, you have to follow some specified condition. But because you are in your house, you are playing with all this. So this is the process. You can try many things, change many names, critique it, and say, no, why do we have to do this and all that? Do you understand me? If you understand, just say hi. So you get, I'm sure that you get what I'm saying. Amazing, 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 amazing. All right, so we've built the process now. So let's see, are we actually getting products, right? So if you come here, this is our product stream, S6, S7, S8. So S6, S7, S8. So you can see that we're actually producing, what is really important for us is the liquid hydrocarbons, right? If you come here, you see the decane, right? We're getting them in S7, right? S7 is my liquid hydrocarbon. You see the decane, you see it here. Do you understand what I'm saying? This is the unreacted gas. So this should have more gas, and this should have more of the liquid hydrocarbon, and this SH should have just liquid water, right? More of water. So you can come here and confirm that does this reaction actually work? So I have a feed here that has all this. Now S6 has, where are the gas streams? You see from methane. You see I have more methane in S6, more methane. Look at my stream. Come here, let me take it around here. This is methane here. There's more methane here and less methane here and less methane here. That makes sense, right? These are more of unreacted gas. So, but as you have more of the liquid hydrocarbon in this stream S7. So if you come to S7 now, I should see more of hexa decay. You see 173.5, 228, we have more of those liquid hydrocarbons here and here. Does it make sense to you? Does it make any sense? Aha, that's what I'm saying. So this is the gas. This should have more gas, but we can, if we want to make the conversion, make it more realistic, we need to put a recycle stream so that the unreacted gas will go back into the feed, get heated up back again, so I can have more of my products. So I can tell you with all assurance that this system that was simulated actually worked. It worked because it produced the kind of product that we expect it to produce. Amazing. But one of the things you can also check for the interest of time is the economics. There are many things we have here. We have, this is the analysis place. This is the energy analysis. This is the economics. Like one thing is to build a plant. Is it economically viable? That's the next thing you need to ask yourself. If you have a pro version of our software, you'll be able to open your results in PDF. So if you see what I have here, it says generate a design report, but you need a pro asset. The free assets cannot give you this. So if you have a free asset, all you can do after simulating this is to now take a screenshot, right, and share it with your people. But you have to rename all this. I didn't rename it, but you have to rename all this to make it industry standard. But I'm watching time because I know we have just 1 hour, 30 minutes, and we need to also play around with how to think like an engineer and give 1 or 2 minutes for questions. All right. So the pro version here, if I click here now, it generates a different tab. I'll show you. I'll go to that screen. It goes to a different tab. Let me show you that. And you see the beautiful thing about having the pro version. Say something in the chat if you see my tab showing the pro version. Awesome, awesome. So you see, it comes out like a PDF. You see it comes well with like a design report. The design report, it shows you the flow sheets. You see the unit operation. This is so good. So this is how you extract your data and tells you the convergence and tells you everything. So this is some of the advantage. And you can print it as a PDF, right? And kind of email it out to whoever you want to show, to say, this is what I have and this is what I don't have. The one other thing I want to show us is this real quick before we do some minute now to. Okay, so I'm going to stop sharing. Let's go to our simulation back. Okay, you see my simulation, right? So one thing I also want us to do, if you are able to finish up all the simulation, or maybe after this, what I will need all of you to do is this. After you build your simulator, you see this, that looks like a globe here. You see that here. You can publish your reports, your simulation report on a gallery. So we've created a community of LensaSim users. So if I click that, it takes it to a gallery, right? It opens a gallery and everybody can view yours. What we want to do here is to make you employable such that when you run simulation and put it on that gallery, you can actually put that on your LinkedIn profile and people can see that and say, oh, wow, you build this, you can do this, and then people can really trust that you really understand process simulation. Does that make sense? So let's do that. Let's do that. I'm going to click this now. I click publish my report. It's published to a gallery already. It said, enter the report in the gallery, add description and this. So we can go to that gallery. How do we go to that gallery? Let me show you. Now, let me go to that guy. I'm going to leave some time for questions, so don't worry. Like, let's do this now. Let me make it in a simple way. So www.lensasim.com. Let's go to the gallery. So you see, okay. All right. So if you go to lensasim.com, just say www.lensasim.com/ do www.lensasim.com/gallery. Thank you. So you see now, it shows my gallery, right? We can actually, we should have done that before we publish. We should have renamed it very well and all that. But you see, you can publish your results here. You can publish your results here, and then we can, you can play around with it. Like people can see your result and then, comment. So I'm trying to build a community of people who use LensaSim. So you publish your result, people can comment, people can see. So we're hoping what we're going to achieve is that when we are going to have a large community that's like hiring managers, people hiring can come to this place and see people's work and then, use that to judge you that if you are good or not. Because what we want to achieve is not just that you can, we want to be sure that you understand this. So when we're hiring people, we can pick from pools of here. I don't know if that makes sense to you. Okay, now let's within the few minutes we have, let's now think like an engineer. I think you're already thinking like an engineer. If you agree with me, just rate thumbs up. You're already thinking like an engineer. You're already thinking like an engineer already. Yeah, I see someone says his own did not converge. I think there might be just something that you've missed as we're specifying it. I will share the content of my presentation, this thing. Oh, awesome. Williams, amazing. So I will share that to everyone so you can, use that to see what we've missed. Okay, awesome. Now, within the next 5 or 10 minutes, let's now play. You've developed okay, one thing. I need to show you the economics on this tab, but the challenge is that if you don't have a pro version, you may not be able to see the economics. That's where that's where the only problem is, but we'll see. But we also have an economics tab that tells you about the economics of what you produce. It tells you it tells you the CAPEX, the OPEX. You see the economics tab is already kind of incorporated into your design. So we've produced LensaSim in such a way that as you run it, as you simulate, it calculates everything. But you can always come and respecify the conditions to what you want. Okay, does that make sense? Sorry, I'm trying to be very time conscious here. But you can go to the economics tab here, and then you can see the output of what you have, the purchase equipment and all that. You can also change things to specify how you want it, right? And all that. Okay. Let's test one scenario and see how we're going to think like an engineer right now, real quick, because of time. I need to give time for people who might have questions before we end today. We may need to have another, I don't know, but the videos will be available for people to go through later to see and then kind of explore that. And you can feel free to reach out to us. The president can share our contact with you. My team will respond if you have questions. But if you go to our website, there's a place to drop questions. That go to www.lensasim.com, and let me let you know what I'm just I'm using our product here to show you process simulation. And I said that the motivation of developing LensaSim is not just only access. Access is part of the problem, but the other problem is, owning the learning system. We want you to understand chemical engineering more, and so the barrier of simulator, that's like, how do I get simulator? That should be taken away from you. So you have the simulator. From there, you can test your chemical engineering skills more. So you see now we played around with reaction, we played around with everything. So imagine you have to calculate all this with your hands. It's going to be very busy. All right, let's paste one quick scenario and see how we can test. Now, let me ask you a question. Quick question. We have our separator here, right? Our three-phase separator is there, right? If you see the PFD, we have the separator. Now, let's assume, now this is how you think as an engineer, say, let's change things. Let's change some parameter and see what will really happen. The question is, the separator is connected and is offline. But what if if we feed 200-degree hot gas into it? I said that we need to cool it down. What if no? And say, let's just feed a very high temperature, like 200 degrees Celsius, directly into the separator. What will happen? This is where you can test those models on your simulator, not on real plants. I have many stories to tell you guys of some errors I've made in the industry. I had my internship in Warri Refinery. I worked in Warri Refinery, but I did my internship. I worked in Warri Refinery, did the internship. I made some error in the refinery, and it was very deadly. It was very deadly. So I was a new intern who just started, and it was the operator, the engineers on floor that quickly came to save me. Maybe I will just say it in 1 minute. There's this particular valve we need to turn every time to drain the liquid from the gas, from the system that we have. Rather than turning the particular way, I turned the wrong way. And you can imagine high pressure in the reactor coming out, boom, and just, it was, high pressure in the system we have. It was deadly. But anyway, that's for another. But now let's play around and see if we change the feed gas into the separator. As I said, so this is the condition I'm trying to say. Maybe should I drop it in the charts? Okay, maybe that might be easier. So this is the question for the student. So if you have your separator now, maybe you can play around with it now. I'll put it in the chat. This is my conditional test 1. So this is the condition. The separator unit is still online, connected, and functional. If we feed 200 degrees Celsius hot gas into it, what do you think we'll get in our liquid fuel product S7? What are we going to get? If I put a very high temperature into it, what are we going to get? All right, so let's play around with that. We're going to play around with that together and see how do we do that. So what you need to do is that where you have that cooler, remember the cooler is cooling into 40 degrees centigrade. No, change the temperature from the cooler to 200. So let's go and do that. We're going to go now and change the temperature of the cooler. This is our cooler here. Are you still following me? Are you following me? Drop something in the chat. Okay, good. Amazing. So now this is the cooler. You see the outlet temperature of the cooler is 40. I want to change it to 200. But before I do that, I want to tell you what we should watch out for. Watch out for. The cooler, look at the outlet coming from the cooler here, right? It's having a mass flow of 3,546. That's the mass that is going to the separator, right? And then you see some of the conditions that we have here, or you can also check from the flow sheet we're seeing at the bottom, or the steam table, as the case may be. Sorry. So now I'm going to change this and see what really changes. So remember what we have before, very important. And then I'm going to change this to 200 degrees centigrade. Instead, I'm going to send a very hot gas into the separator. And now after I do that, it tells me that I've changed things. So I need to rerun it. Let's see if it will converge. Wow, it converged. But Converging, is that all that matters? No. Chemical engineering is not just that, because chemical engineers, we're not really software engineers. Software engineering skills is good, right? But we're going to use this thing to make engineering decisions. That's what we want to learn today. So we see that we're going to prove that, can we do that? Does that make engineering sense, right? So that's what I want to build into us, to the curiosity mind, to play around with things. But like I said, you can't play around with real plants, right? You can play around with your simulator, because simulator is the closest you get to reality. Yeah, all right. Okay, I've changed that. Now let's see what is the stream coming out from S5. Okay, good, good, good. So what are the products that we have right now? So let's check our liquid hydrocarbon that we get now. So go back to your S7 now. Oh, I'm watching time now. I will need to stop quickly. So look at your liquid hydrocarbon that you have, your S7. Look at this: butane, hexane, decane, nonadecane. You see the value you have now, right? Do you still know what the old value is? Is there any change? Are we getting more liquid hydrocarbon or less? Right now, we are having very low, right? Oh, no, sorry. Let me change it to mass flow. Sorry, I beg your pardon. So you see it well. So you see what are the changes that we're seeing now. So you have this. So if you go back now and change it to, okay, my apologies here. Okay, good, good, good. If I put it back to 40, I want to show you that the changes that we're seeing. This is 40 now. Are you seeing any change? So you had 94.8. So you're going to play around and check these values and see what difference is it giving you, 94.89, and compared to, is this going to change? Is it not going to change? That's how engineers do, right? You try things and see. Now we're having 94.89, 28.17, like that. So you do that. No much change, right? So that's how you're going to begin to think like an engineer. You're going to begin to play around with things, change parameters, and see what really happens when you do that. Does that make sense? I think what I'm trying to achieve here today is ability to play around with things, not just going with the status quo. That's where I'm going. Can I change parameters and use that to see what economic sense does that make? What sense does that? That's what I'm trying to achieve, not the values, the sense in doing that. So let me go back now. I'm going to change the conversion. Remember, the conversion that we had was okay, maybe this will be more practicable now for you guys, actually. Let's do this. This will make more sense. But before I do the next challenge, I will go back now and change my temperature back to what it's supposed to be. My cooler, I'll put it back to 40. I'll put it back to 40. Okay, good. Now, let me put the second challenge that I want you guys to try. Second question is, if our reactor efficiency drop by half, where does all the unreacted carbon monoxide and hydrogen goes? Does it just vanish inside the reactor? So that's the next question I want us to try. This will be more practicable for what we are trying to understand today, to see how we can think. Don't just take things the way they give you as face value. You can question yourself, okay, 70% conversion. Okay, what if I just change it to another amount? What effect will it have? That's how engineers do. You do critical thinking and use that data to redesign a different plans that will give you what you want. Okay, all right. So let's try the second one together. We want to change the conversion. The reactor conversion efficiency has dropped by half. So rather than having 70% conversion, we're going to have 20% conversion. Sorry, no, 20%. That's not correct. Am I right? It should be 35 now because it dropped by half. So instead of 70 to now be 0.35. Did you get me? If you get me, just say drop down. Good. That shows you are following me. Amazing. Amazing. Okay. All right. So let's go now. I want us to see the liquid feed first before we change it, right? Uh, this feed that we have here, I beg your pardon. S7, right? Please take a look at what we have in S7, right? It has a mass flow of 513.5, right? That's what we have with 70% conversion. So if the conversion is low, what will happen to this? Will it change? Will it be the same? Am I going to have more gases than liquid? So let's do that. Let's go back to our reactor here now that we have. Remember, can somebody take a note of the value that we have here before we make any difference? Let's come here. Can somebody take a note that the mass flow we have here is 513.5 kilograms? Somebody should just take a note of that somewhere and say, okay, this is what we have. This is rough estimate of what we have. Let's see what will change. I change my reactor now and come here. Rather than having this 0.75, I change it to 0.35. Then my reactor is not working at full capacity, it's working half. And then I click a run. Converge. Good. So now let's go and check stream 7. Boom. Did it change? If it changed for you, let me know. Just drop something in the chat. If you agree with me that we are now having less. Amazing. Amazing. Thank you. Okay. Let me stop here in the interest of time with this simulation. I want to be very time conscious with you guys. And I will go back and share my slide now. And if you agree with me, we have been able to successfully build a Fischer-Tropsch process. And then we've played around with how engineers think, right? Curiosity, being able to put, change values and be able to play around with those values and see what are we going to really get. I didn't have enough time to really delve more into CapEx and OpEx, but maybe next time, or if you want more, if you go to our YouTube, my team can drop our YouTube channel. We have trainings that were already made and more that we're going to make to help you understand all this. Like I said, our LensaSim is free for students, right? If students, you don't need to pay to be able to explore, but there are limitations, right? That's what we're seeing today, right? There are some things you cannot do if you have the free version, but the pro version is paid, $5 per month. $5 per month, and there's also a discount. If you go to our website, you see all those details. And then we also have things for the university, right? So imagine what we're trying to do, right? We are trying to provide access such that professors are able to teach process simulation easily. On our website, we have a way you can create a class as a professor and then teach this course. Your student can join anywhere from the world on their computer. They're learning the simulation, and you can actually create a class, set assignments, and our system can help you to auto-grade it as a professor. So we take away the barrier that you get as a professor, whereby you're going to say, how do I set assignment? Our system would help you. You can teach the class from the comfort of anywhere you are, and your student can join anywhere. They don't need to do all those complex installations that legacy softwares actually have. Okay. I also want to, talk about the team that are behind all this. These are my team here, Dr. Peter Oladipopo, who is our executive chairman. I am actually the CEO of the company. And then you have our other team, Dr. Moses, who is a professor in Oklahoma State University of Oklahoma. I'm sorry, I keep missing that. And then you have Dr. Vignon. We are all UNILAG alumni, and the three of us finished from chemical engineering. Our very good friend from the years, finished from system engineering. And these are the three teams behind Lensa Technology. This is where I will draw a curtain. Thank you so much for taking time. I will be able to take, my team is available, not just me now. My team is available to take questions. So they say, Dada Oleja, Olento Bojule. So sorry, I'm speaking Yoruba. If you throw a question I don't understand, so I've called them out, right? You see all of them. They are there to help. There's a professor amongst us, professor. There is Peter, the Dr. Peter Oladipopo there. They're all there. So, but let me stop sharing. Thank you so much. I pass it back to the organizers of this. I can take one question in the interest of time. Thank you so much.
Thank you very much, Dr. Ibe, for such an insightful and practical session. Thank you so much, sir. To my fellow chem geniuses, I'm sure that everyone here has learned something valuable about process simulation and how engineers approach real industrial problems. So we'll move into the questions and answers session now. If you have any questions, please raise your hand using the raise hand feature or type your questions out in the chat box. So Dr. Ibe, some questions were dropped during the session. I'd like to read them out first and then we'll continue
Okay.
from there. So the first
Okay.
question was actually dropped by Mr. Moses Olayemi. Can we actually use any personal email or does it have to be university email? Because I noticed that when I used my student's email, I could add more than 10 components. So I wanted to ask, can we use
Yeah.
a
Thank you.
personal email?
Thank you. That's a very good question. So first, to sign in, you can use any email, but the features that you have is a function of the kind of subscription that you have paid. Like if you have a free session, there's a limitation. So it's not your email that determines the features you can explore. The email just give you access to the simulation, but the feature that you can explore is a function of the package that you have signed. So if you have a free access, the free access has a limitation, right? But if I had the pro access, I paid for pro, I have more future. So I being part of the executive team of the company, right? So I have more, so I have like an enterprise version, I have a super, so I have more features than use, right? So exactly, it's your email does not determine what you can use. The email gives you access to the simulation. So any email will give you access, but the features that you can explore is a function of what type of subscription do you have. Is that clear?
All right, sir. Thank you very much for that, sir. Another question from Fadilulai Adeni. He asked, please, are there situations where an error message gets displayed and what could prompt that? So,
Well, error message can be anything, right? It depends, right? So that's why, first of all, that's why it may be that the conditions are not specified the way you should specify. That's why I'm going to send that document to you guys so you can explore it. And it can also be that, again, sorry, but before I say that, we have an AI feature incorporated, but that is not for the free version, sorry. We have an AI feature incorporated. So the AI can also help you if you're confused. So what the AI does is to help you through the process when you are confused and also help you to interpret the data. Make sense? So the error message, and that's why we have to explore, right? Once you say error message, you're going to play around with it, but feel free to, it's not something that we can really solve right now because of the limited time that you have, but you can feel free to send the error message to us. We will get back to you. We pride ourselves as a team, a company that responds within 24 hours. If you send the error message to me, to our team, our email address, I think my team will drop our email address where you can contact us, right? The team. So you contact us, we're going to respond and help you fix the problem, right? Okay, does that make, I don't know if that's helpful, but yeah, error can be anything, but if AI feature can help guide you through the process. But if not, if you don't have the paid version, you can send that to us. We'll help you. We would encourage you to try the pro version such that you can use the AI to explain all this. All right. I don't know if that's helpful.
all right, sir. Thank you very much, sir. I can see the reaction from him. Means his question was answered. So another question from Williams. For the economics section, are the prices of
Yeah.
all components fixed, or it's all updated in real time as it is in the current market? Also, is there a feedback section that shows us where we went wrong in our simulation and goes further to tell us where and how we fix it?
Good question. So the economics is calculated based on estimate of the market, right? But like I said, you can change it to suit what you want, right? You can go to literature and pick things and put it there and change it. But all the conditions that you have specified, our simulation is going to use that to determine the economics for these plants based on what's available in literature. But you can also critique that and say, no, I don't accept this. I want to change the size here. I want to change this one. I want to change, so you can play around with that. Okay. Sorry, I missed the second part of the question. Sorry, Docas, can you say that? Apologies.
Okay, sir. It says also, is there a feedback section that shows us where we went wrong in our simulation and goes further to tell us where and how to fix it?
Oh, yeah. So it's going to bring out an error, right, when you are wrong, right? It's going to bring out an error when you are wrong, and it will tell you really. It will tell you again. I don't have the free access, so maybe. But the problem is that the free access has limitation. Get me right? But so it could tell you where you are wrong. If you put the guide on, the guide might be able to guide you through the process, and then when you run the simulation, it brings an error. It might be able to tell you, it suggests situation for you that this is where the problem is wrong. Oh, you didn't specify, you didn't specify that. It could tell you, it could give you an idea. But again, if you have a pro version, it would point, you can put it in the AI, you write a question, oh, my system does not convert. Can you tell me what the problem is? It tells you where the problem is. And if you don't have AI, you can reach out to us. We are your AI and we can help you fix it. But yeah, it would suggest to you. But let me know if that is not the case, then we can work on that to make it more flexible. All right.
Okay, sir. I'd like to read out the next question. Okay, about free version limitations. The students have to pay for the pro version, or is the campus slash enterprise license something that UNILAG can subvent for all the students? I was going to ask that
Yes,
too. Is it
yes,
possible?
yes, yes. We want to. So we're currently where we are with our companies, that we are currently now just like testing it. By next month, we start selling. We're still going to contact professors, right? We're going to contact the HOD of the department. I'm going to send him an email. Yes, the university can. That's where the enterprise version. University can pay for the university, for the department and the students. So it tells you the number of students that can use. So you have all this feature that I have, more than this limited. The university can pay for that. And it's quite cheap compared to what you get from ASPE. It's quite cheap, right? And you see how our feature is easy to use, world class, up to date. So we will work with the department, right? We'll work with the department. I'm going to send an email. My team rather is going to send an email to the HOD, and we'll find a way to talk to the HOD. Yeah. We're going to sell the enterprise version is for the universities. So the universities are going to have to pay for the students so that students can use it. But students can also get their own access, right? Just $5. All right. I hope that answers the question.
Thank you very much, sir. And would like to take the last question from Adeoye Ayomide. Please unmute yourself and ask your question. Thank you.
Thank you very much. Thank you very much, sir. Good afternoon. And I want to say a big thank you for a fantastic session on the process simulation. A big thank you to you and your team. Now, my question goes to us. I'm a 400 level chemical engineering student, and someone, someone that is preparing for the industry, I've been reflecting on how we can be using this process simulation tools in practice. Now, I noticed something while being on IT, that while these commercial packages like the LensaSim, Aspin, and some other things, while we can use them, but majorly all these IOCs or NOCs, they have their own in-house or tailored kind of models that they use. So as a student who cannot really learn every software package, in the market, how do you advise one to actually master the algorithm thinking or the underlying patterns behind all these things, so that even if you meet any package at all, you'd be able to still excel with it, basically? That's my question.
This is amazing question. Thank you for asking. And that does not mean that the rest of the questions were not amazing. Every question asked here today is amazing, world class. Yeah. You've asked a very sensitive questions, and I have actually sat down many times, even last night, thinking through this type of question that you're going to ask. And my team, I'm going to respond, and then I can give opportunity to one of my team members to also chime into that. Any of my team, I have all my 4 teams are here today. So the idea of LensaSim is not to help you to learn a software. That's not what we are trying to achieve. The idea of democratizing process simulation is for you to gain a skill. And the skill is to be able to think like an engineer, not just what we want to achieve is not just that, oh, I can use LensaSim. The question is, I can use LensaSim to understand chemical engineering very well, understand process engineering, such that if I get to any industry, and this is the kind of simulation they have, I am able to use my understanding to critique things. I don't know if that makes sense. What I would focus on as an engineer that is looking for a job is not to learn multiple software, is to build strong chemical engineering skills and use software that are available to understand it, so that if I find myself anywhere, I can make engineering decisions, even if you tailor this. I still work as a process engineer, right? And there are other softwares that we also use. You get so, but what is important is my engineering critical thinking skills. So if we take away the problem of access from you, so you have a software that is available for you to use easily, you can begin to build that skills of critical thinking more, and then you can get to the industry and get a job easily. But what we are doing in LensaSim with, that's also trying to build a community, right? Just like you have a community of GitHub, like that. So such that if you put on your LinkedIn that you have the LensaSim skills, people know that you can think like an engineer. I will leave opportunity for my team, any of my team members, to chime in case I missed out anything.
No, that was spot
can you
on,
guys
Dr.
hear me?
Omodolor. Yeah.
Go ahead. Sorry, my two team, Dr.
Go
Peter.
ahead, Dr.
Can you guys-
Oladipo.
Yes. Yes. Who asked that question?
Yeah, Ayomide asked the
Can you guys
question.
hear me?
Yeah,
Yes,
we
yes.
can hear
Okay,
you.
let me just quickly introduce myself. Yeah, I mean that's an excellent question. So my name is Dr. Peter Oladipo, right? Dr. Omodolor has done a fantastic job explaining, answering that question, right? It's a fantastic question, right? So you are wondering, how does, for example, using NSChE apply to other process simulators? The truth is what Dr. Omodolor said. You don't need to learn 5 or 7 process simulators, right, to be able to demonstrate that you know process simulation. In fact, all you need is just to master one, right? So that's the goal of NSChE. You want to learn, what you really want to learn, what you really want to master is process simulation itself, irrespective of the tool you are using. Right? So that is the underlying skill set here. Process simulation, either with LensaSim, with Aspen Plus, with ICs, with the WC, whatever. Right. So when you are using LensaSim, what you are doing is you want to. So it's important that you are thinking through the process. That's why the title of this webinar is thinking like a process engineer. So you are not a robot just putting one unit after the other and running it. You have to think through the process, like what the facilitator has said to the Dr. Omodolor has told you today. You have to think through it. Why am I connecting one unit after the other? Why am I using this condition? Can I change it to this? So once you do that, okay, once you go through that process, you can think, you can understand why you are doing one or another. I tell you for free, you can use one if you have found in any company that is using another package, you know what to do. You just need to get started understanding their own environment, and before you know it, you are good to go. So you understand why you are choosing the property method, you understand the underlying theory behind it, right? And a good thing with LensaSim is you will notice that as you're using it, there are some theoretical explanation. You see some explanations that you can follow, you can read through them and see, okay, this is why this simulator is suggesting this, what is why it's telling us to do this. So those apps, those guides you to understand why this is done this way. So and that brings us to what we are trying to problem we are trying to solve LensaSim. We are trying to give you the answer so that you really have, because these commercial simulator indeed are expensive and you don't even have the answer. Like what you said, it's when you get to the IOC, then you realize that you have this software that you have to use. So LensaSim gives you the answers ahead of time, right? You see it, you are able to use it. At least you familiarize with an environment similar to what you encounter in the industry. So just get apprise yourself with LensaSim, and I tell you, you strive in any environment you find yourself.
Amazing. Thank you. Any other contribution from any of my team? Are we good? Okay. Thank everybody. So all right. So yeah, that's it. I think we've answered the question. We'll give it back to the coordinators and I also want to thank you. Before I give back, I want to thank everyone for joining today. And special thanks to the organizers of this event. This is fantastic. And all the students who came in today to join, learn with us and ask questions. Thank you so much. And this is the end of my presentation. Over to the organizers for any other reaction before we close for today.
Thank you very much, sir. So Ajoke Ade Folashayo asked 2 questions. The second one has been answered, but the first one has not been answered yet. So I wanted to call your attention to it. She asked, is process simulation an active skill used in Nigerian chemical/process industries? Okay, this question just shows that she didn't join at the beginning of the call, but just to summarize everything, could you please please go over
It's
it
fine.
again for those who joined later, sir?
That's fine. That's fine. Yes, the answer is yes. It's a skills that you need to really build. And like I said, one of the slides I went through, why do we really simulate, right? I said it helps you to test concept, right? You want to build a model and help you, because the closest you will get to industry before you get to industry is process simulation. Think it that way. Or think it this way. Imagine you are an architect. You want to build a house, right? You need to draw architectural drawings, the 3D first. When you have the architectural drawing, you draw the architectural drawing. When you have the architectural drawing, before you go ahead to build the house. Does that make sense? All right. So you can't just say, I want to build this house and go and build the house. But from the architectural drawing, you can say, should this beam be like this? Should this be like this? Should it be like that? Those are all the things you are going to use to test first before you go ahead to actually build the house. That's how process simulation is. Process simulation is like you trying to see that structure visually first before you build that. So that's an essential skill that employers will look at. That can you think like an engineer, right? Like I said, we're not learning tools, we're learning how to think. So you use that model to test things first before you can go ahead to build it. I hope I explained it. I hope this was well explained. If not, let us know. You can reach out to us personally. We can explain more.
Thank you very much, sir. Thank you so much for your time. Thank you so much. So for my fellow chem geniuses, if you have any questions, please reach out to them via lensa@lensatech.com. And this brings us to the end of today's session. If you're excited, can I see your reactions, please? It was a very, very insightful and practical session. So on behalf of the NSChE UNILAG student chapter, I would like to sincerely thank Dr. Ibeh Omodolor and his team for taking time out of their busy schedule to share knowledge and experience with us. We are incredibly grateful. We are grateful not only for today's presentation, but also for your commitment to giving back to your alma mater. I'd like to say a very big thank you to everyone who joined today's webinar. Your participation is what makes sessions like this meaningful. Thank you so, so, so much. And we hope that today's discussion inspires you to continue exploring process simulation and the exciting opportunities available within chemical engineering. On this note, I'd like to call it a day. Thank you so much, everyone.
Thank you. Bye for now. Okay, bye. I leave now. Bye.